So I'm going to talk about the Wakefield acceleration. So that's the topic I was working on for a couple of years, maybe like 10 years. So I want to talk about the basic concepts, some like theoretical background, and just give you some overview of the field in general. So yeah. So the outline of the talk. So first, I'll just introduce the word Wakefield. So what this is, it's kind of connected to the classical electrodynamics, the way we know it. So it's a fancy word, but it's kind of nothing very special. Then I talk about the Wakefield Accelerator. So what is the Wakefield particle accelerator is, the basic principles, and then the basic theorems, the fundamentals. Let's put it this way. So how you can estimate the parameter of this machine. Then I'll show you where we are, like experimental wise. Then I'll try to outline main challenges and conclusions. So I have a lot of slides, but I'll try to fit it into the 40 minutes I have. Okay, wish me luck. First of all, so what is the Wakefield? So, and let's start basically from z-axis, right? So let's consider a z-axis. Then let's consider a charged particle, which is driving along the z-axis with a velocity v, right? So then let's consider the particle which is driving right behind the first particle, the yellow one, with the same velocity. So how those two particles interact? Well, obviously, so it's a Coulomb interaction, right? So just due to the self-field, if those two particles are driving in vacuum, that's basically the only field that we know, right? The interaction length is 1 over gamma, where gamma is a relativistic gamma factor, and the strength of this field is 1 over gamma squared. So now, if those two particles start to drive close to the speed of the light, which is a common thing when we consider acceleration of the particles inside a particle accelerator, because the particles pretty quickly become ultra-relativistic. So the interaction due to the Coulomb field basically vanish. So when those two particles do not interact anymore. Is there anything else? Well, sure, we know. So if I'll introduce any type of a medium, obstacle, whatever, right, that will make the first particle radiate, then this radiation will interact with the particle which is going behind. And the radiation due to the interaction with this boundary that I have here on this slide, so is basically called the Wakefield. So to summarize what the Wakefield is, it's a special solution to the Maxwell system. And usually the steady state Wakefield, and usually it's called, the whole thing is casted in a framework of so-called wake potential, which I'll introduce a bit later, is basically described by just this function W, which is a function of two spatial coordinates, x, y, and z minus vt, right? Because everything is in the frame, it's not convoluted frame. It's just, we postulate that we are interested only in the solutions of the Maxwell system that have this symmetry, the translation symmetry. So it's some sort of a quasi-static picture, if you want so. Sources of the Wakefield. Well, as I said, that's any type of a radiation. In the accelerators, it's like these loaded structures, like some sort of like connections of the vacuum pipes and so-called structures with the retardant layers. It's dielectrics or small corrugations or whatever. So actually any roughness, anything which is non-ideal will cause the particle to radiate. So,
Stanislav, sorry for interrupting you. I guess there is a question from Andrei Bogdanov. Andrei, please.
Yes, I'm sorry for the interruption. Am I right that the main idea that the moving particle has a near field, and then the idea is this near field could be scattered by some obstacle to the far field?
Yeah, you can think of this way. Absolutely, right. Because again, like once you accelerate the particle, right, so you don't have the interaction along the z-axis, right? Well,
absolutely.
You can scatter the field and then like translate it back to the trailing particle, right? So that's why it's a Wakefield, right? So it's a backward interaction. So the trailing particle cannot act on the particle which is going ahead of it, right? Because of the causality, and but the head particle can act back.
I see. I see. Is there any difference between like a Smith-Purcell effects and the effect that you would like to consider in your talk, or it is the same? Smith-Purcell.
Or I was about to say that. So basically, the Wakefield, the framework, includes all type of radiation, right? And let me see. So that's the formal definition. So you have like solved, for instance, some electromagnetic problem, right? Then the wave potentials, the way they introduced, they usually define this way. See, you just integrate the Lorentz force, right, with this substitution, and then you have a so-called wave potential. And this thing will have the dimensions of the potential, actually. So it's kind of quite convenient. And especially in a quasi-static picture, when you have like the first and the head and the trailing particle traveling through the smooth and translational symmetric system along the z-axis for quite some time, when you have like a stationary process, like when you reach the equilibrium. So that's those formulas are simplified, and you can actually make this. Let me see. You can do this substitution. See, so like that. So now all your fields will depend on z minus ct, right? And then basically the wave potential is a rescaled field. So and then here on this slide, I have like the longitudinal wave potential. And the transverse wave potential, it's a bit counterintuitive, but the transverse wave potential, the way people introduce it, it's actually a vector. So because it's,
I see.
Because this guy is a transverse Lorentz force, right? See, basically, it's the only component for the longitudinal Lorentz force.
Having vectorial potential, it's a bit unusual, but
absolutely. So it's a bit confusing, but I guess the idea here is, so say you want to consider so if we're talking about the momentum, right? So the modifications to the momentum of the particle. So like as for the longitudinal momentum, it's okay, it's fine, right? So it's a scalar, but the transverse momentum is a vector, right? And then just, to keep the same convenience, like with the energy change, right? You want to say that you want to consider the transverse momentum change, right? So that's why you introduced by the analogy the vector potential, but which is not really vector potential, some sort like that. And another remark.
I think Andrei has another question, right? There was another question from Alexei.
Yes, I'm sorry. I maybe a second silly question. So usually, as I know, when we consider like electron beam interacting with some like periodic structures, when we have Smith-Purcell effect, usually we just neglect the interaction between electrons because it's quite weak. Am I right? The effect that you will consider, they are weaker than the Smith-Purcell effect usually because it's based on interaction of two electrons.
So here in this sense, the Smith-Purcell will be the main contribution. So then you'll just connect all other effects but the Smith-Purcell. So you basically plug in your field, Smith-Purcell fields into those formulas, and that will define the waves.
Electron interaction are weaker than interaction with the surrounding media.
Right.
Okay.
Right.
Yeah, I see. Many thanks. So I'm finished.
Well, it really depends, right? So it's not an approximation. Okay. So, but usually this is the case. But actually, the framework allows you to account for those weak interactions as well. And if you want to have this as a correction or some additional thing, so usually the interaction due to the scattered field is larger. So that's how it works. So yeah, and another remark that I wanted to make, just because you have like when your particles are relativistic, right? When the gamma is large, so there is a decoupling, at least in the zero approximation, between the longitudinal momentum and the transverse momentum.
Right.
So they kind of decoupled, and that's why it's kind of like easy to introduce.
There is a question from Losha now.
Yeah, Alexei Sherbakov wanted to ask a question. Losha, please.
Yes, thank you. Just a small question regarding the Andrei comment of near and far field. What are the characteristic scales and numbers in the problem?
I guess no, like really scales. It's everything is defined by the gamma, I guess. So, but as I said, I mean,
yeah, it seems that there should be some characteristic wavelengths and how they compare with structure, for example, geometric scale.
Well, I mean, so Well, to be honest, right? So I just introduced this very large gamma to connect the whole thing to the radiation, right? Like what people usually do, they can account for the weak interaction for the column field as well. So I mean, there is no restriction on those formulas. So if you want to include like interaction between the electrons, like column field, you may include this as well. But then there's going to be like a mixture of different affects, which is acceptable. And in numerics, for example, when you solve the problem on a computer, just from the first principles, basically the wave potential usually includes all the affects, including the interactions between the electrons. So when you do the particle and cell simulation, so that's what you usually get from the from it. But because in this talk I want to focus more like on analytical estimations, that's why I want to get rid of the interactions between the particles, because it's usually it's a mess.
So you said that.
Okay, and maybe you comment what spectrum in this problem do you have? What is a spectrum?
We'll discuss the spectrum later, or
okay.
Spectrum, you mean
spectrum of the emission?
Yeah.
From 0 to infinity, right? Well,
yeah, but there's
a cutoff. There's a cutoff because of it's usually a waveguide, right? So the channel usually defines the cutoff frequency, the lowest frequency, but then it goes up to infinity. Because if we're talking about the Green's functions and the wave potentials, could be Green's functions. Because if you're looking at one single particle, you can easily put together a Green function and then do this convolution technique as we know it. So I guess and if we're talking about the point particle response, then it goes up to infinity. Well, of course, there's a decay, but the spectrum is like for the non-dispersive mediums, for instance, if we're talking about say dielectrics or like solid states in general, then it could go up to infinity. If you have like some frequency dispersion, then it depends on the frequency dispersion, right?
So I think we as like this metamaterial, nanophotonics, and radio physics community are very interested in the spectrum. So how, if you would, maybe not now, but just at some point show like any spectrum. So that's what, because we can like make any design, any resonator, just give us spectrum and we will give you back the design. We need a spectrum.
Yeah, this is what we are talking about. We are talking about equation, or we are talking about physical problem.
Yeah. So no. If you want to talk about like the numbers and like what is usually say the basic frequency of most of the structures that people use, it's usually in the terahertz range. Mm-hmm. So that's what people consider. Mm-hmm. So it's like 1 to like several terahertz, and that's the main frequency of interest. Mm-hmm. Just for different reasons, because people make terahertz sources based on that, and it turns out that the terahertz range is best from the just engineering perspective. So you can't go to higher frequencies because everything becomes very tiny. But if we talk about say plasmas, which the whole formalism like that will work in plasma as well, with certain modifications, of course. But there, the frequency, the base frequency could be higher.
Sorry that we're stuck here and we still asking very simple questions and naive. So to have this terahertz, you need to have a structure with the proper period, around. If you want to tune a terahertz, or you need proper energy of electrons, or what?
Well, we're talking energies about from 10 MeV range and up, right? Usually, what people are talking about is like GeV energies, and like talking of experiments that people usually do. So the lowest energy people use is about like 40 megaelectron volts. And so at Stanford, for instance, it's 23 GeV.
And how does it correlate with the electrostatic approximation you have it here, right? Or am I wrong?
It's not electrostatic; it's like quasi-static. Because what do you do? You replace the time, right? So you couple the z and time, right? Why? Because you have a translation symmetry. So if you assume that those two particles are driving inside this thing for like infinitely long time, right?
Yeah, but you introduce potential, which and your force, but your force might not be conservative.
Well, it is conservative. Surprisingly, you can prove that in quasi-static picture it is conservative.
Yeah, but doesn't quasi-static picture fails when you consider electrons close to speed of light velocity?
No. So in this picture, in this framework, no, it doesn't break. I mean, like, listen. So like what I'm trying to tell you, that EZ and F are taken directly from the solution of the Maxwell system. You solve your problem like the way you know it, right? So just, and you have like, well, think of it like that. So you wanna, like, let's go back, right? So,
1 second. Yeah, please.
Let's go back here, right? Look at those two particles. What is the assumption? What is the main assumption here? Those two particles are driving with the same speed. This is important, the same speed. So if you have your wave driving with a different phase velocity, right? Then they do not interact with the particle, right? That's an integral effect. That's why you introduce this potential, right? So you kind of integrate all the interactions from the waves with the different phase velocity, right? So it's like the phase law. And that's how this quasi-static picture appears, because you look at the interaction between those two particles, and the interaction could be casted in this like quasi three-dimensional space, right?
So Stanislav, a question from myself. I wonder if this representation with Wakefield potential holds only for the case of continuous translation symmetry, or it also holds in the case of discrete translation symmetries, just to understand.
Well, usually people do not consider discrete translation, so they just say that it's a continuous symmetry, and that's the approximate. That's at least that's the way people introduce it. But I think, I don't know. I can't really tell right now. I'm afraid that this approximation with a discrete translation symmetry may break, but I don't have an answer for it right now.
And so we have another question in the chat. So if you do not mind, you can answer it.
Yeah, sure.
Right now. So question from Ilya Deri. Did I get it right that in order to accelerate some particle, we should already have a particle that is moving faster than the particle that we want to accelerate?
I'd say that both particles have to have the same energy. So that's what we're starting from. So you would be like, okay, so I'm confused, right? So to accelerate particles, I need an accelerated particle. So what's the deal? Yeah. What is the point? Like you're trying to, this is some sort of cheating. Well, I like the way the seminar actually goes. So it's not like I'm just me talking, right, and showing you pictures.
Yeah, but we just sorry for the format, but we just wanted to get it before.
No, I like it. Let's do it this way. So listen. So this is the picture. Like it's a cartoon picture of like this Wakefield Accelerator, right? So you have like your driving beam, you have your trailing beam, and then you have this is the plot of the EZ. So what's the deal? Say you can create, and I have this plot on the right-hand side, right? So where the electric field EZ on the axis, and I see that both beams are going along the same, like just right straight in the center along the same axis. So, and I have this like blue line. This is the electric field, right? So see here, like I prepared the driving beam in a way that the accelerating field, right, on this beam is lower than the accelerating field on the trailing bunch. So if I will consider like a very simple toy model, what does that mean? That I can accelerate the trailing beam to the energies higher than the driving. And you're like, how that's even possible, right? Because that breaks energy conservation law. Okay, so it will not if I have my driving beam with a much higher charge, right? So if Q1 is way larger than the Q2, so then there's nothing wrong here. So energy is conserved, right? Actually, it's very inefficient way, but so what?
So there is back action, but it's negligible. That will be negligible.
No, there will be no back action. So it's like I can listen. So in this picture, right? So I can basically what is the ratio roughly, right? So it's about like 7, and then we go like what it's maybe it's 6. Well, roughly 3, right? Let's say. Right. So the ratio is roughly 3. So if I'm starting at say 100 megaelectron volts, so then once the drive beam will be completely decelerated, right? And there is no slippage and there's no dephasing, the whole thing will remain the same, right? In a very simple scenario, then the trailing beam will gain the energy 3 times higher than the initial energy of the driving beam. Means that the trailing beam, if they started at 100, then the trailing will have 400. So what's the catch? I mean, right? So you have 400 here. It turns out that the higher the energy you want to get, right? So the more and more length of the machine you need. Like modern accelerators, they have like what, about 20 megavolt per meter on accelerating gradient. And that means that if you want another 100 megaelectron volts, so you need to build like longer machine, right? Longer, longer, and longer. So, and if you want very high energies, then your machine will be like several kilometers, right? So here, because you can bump the accelerating gradient to like gigavolts per meter, again in a terahertz range, because the aperture is about like millimeter in structures. This means that you can have way higher gradients, and having this like trick with the which is called usually like this ratio between accelerating and decelerating field is called the transformer ratio. And having this quantity large, you potentially can accelerate the trailing beam to the GeV energies, starting from only 100 megaelectron volt. So what people usually call this technology so-called afterburner, or like something which you put at the end of your conventional machine. So consider this as a cost-effective upgrade for the existing linear accelerator, for example. Mm-hmm. So I don't know. I hope this this answers the question.
Yeah, I think this partially. I mean, that makes it more clear to me.
So and this covers basically like the way the Wakefield accelerator works. So you have your drive beam, you have your trailing beam, and then you arrange this situation. So again, and in structures, which means that you may have like based on a Smith parcel or Cherenkov radiation, or like how people do like sometimes they consider photonic band gap structures and different metamaterials. So you may have usually the gradients, and those gradients were demonstrated experimentally from 100 megaelectron volt, from 100 megavolts to 1 gigavolt per meter. And in plasma, you may have like 50 gigavolt per meter, which is crazy. Like on several centimeters, you can actually create like a, well, GeV class accelerator. And the cool thing about it that now your machine will be compact. At least that's the selling point. That's what people well, usually say when they talk about the Wakefield accelerator. So now your machine will be like of the size of this room, and this will be like half of your collider, right? And then basically like 2 rooms, and you have a Higgs factory. Oh, like okay, no, you can have a Higgs factory as of today using this technology with this technology, but that's the selling point. That's what people you know, function for.
So, but the dielectric, when you mentioned the primitivity of dielectric, right? So, do I understand right that all happens in so where is dielectric here?
Huh?
Dielectric. Where is dielectric?
Oh, this like what?
The credence or what?
Yeah. The outer layer is copper, right? This gray, yeah, gray one, and then the second layer is basically dielectric layer.
But everything happens in vacuum, obviously.
Oh yeah. So that both particles are driving inside.
Why do you need this dielectric there?
Oh, just to generate Cherenkov.
Okay.
So the first particle generates Cherenkov, right?
Yeah.
So then, because of the reflections, it's got refocused to the trailing particle, right? And that's how I transfer the energy from the first punch to the second punch. So the trick here is it's some sort of an energy extractor, if you want to. And because of the trick with the refocusing, right? The way that I can like amplify the electric field at the position of the trailing beam. So that's the whole idea.
Okay, sorry, I just probably missed the beginning.
No, that's good. All right, so I guess we covered like the way it works, and now we'll talk about some main parameters, right? So what are the main parameters? We briefly mentioned them. So that's the ultimate gradient, right? And the transformer ratio, basically the ratio between the decelerating field and accelerating field. So the higher the ratio, like say I can, like the higher the energy of the trailing beam when the drive beam is completely depleted. Mm-hmm. And the efficiency, well, I don't think I have time to talk about the efficiency because it's the big deal. So yeah, that's a joke. I think you'll like it. So how to approach a problem, right? So we like finite difference methods. Well, clusters, they're not uncommon right now. So okay, laptops, cool. Everybody have a laptop today, right? But sometimes you can still go, old school, right? And you'll ask me, like, why go old school, right? Just because of that, probably. Well, not because of that, because sometimes, you know, to go to the cluster, right? So you have to, you know, take a pen and paper and, you know, do something, right? And understand like what's happening. Then do some estimations and only then go to your, like, you know, big tool and a huge cluster and start the first principle simulation. Just to make sense out of the first principle simulation, you still need your pen and paper and, for the most part, a laptop. Anyway, so this is how you can estimate the upper bound for the gradient. And this is more or less universal thing. I hope so. At least I haven't found, as of today, any other proofs so that this thing is not going to work. So what's the idea here? So I'm going to talk about dielectric because it's just way simpler. So you have your particle driving with the speed of a light inside the vacuum, right? You have your dielectric, which is this yellowish color, and these cartoonish red lines are basically representing Cherenkov cone, right? So the cell field is compressed into like a so-called pancake that's just on a plane, because from the maximal system you can see that the solution is just a delta function. So it's just a delta layer, and then you have this cone going backwards, and then it's going to reflect. So the question is, can you calculate the losses? Is there any like universal way to calculate the losses to the radiation in this case? Yeah, it turns out yes, you can. And basically it's Gauss theorem, Ampere's law, whatever, like any equation from the maximal system will serve this purpose, because it's, you know, the observation is kind of idiotic. So first, so
excuse me, may I ask a question here?
Yeah.
So it's okay. It's written Relativistic Gauss theorem, and in the first formula, should there be not just V, but V over gamma, because of the relativistic effects?
Oh, you're in a rest frame.
Okay.
No Lorentz transformations. No. Rest frame. So the trick here is, remember that, right? So see the Z minus VT. It's not. So this is the main confusion about the Wakefield, right? So people think that I'm switching to the co-moving frame while I'm not. So because of this interaction between those two particles, right? So I have this translation symmetry. If I assume that those 2 points are fixed in time, like in time and space, right? Then the only thing that matters is the distance between the points, right? And that's how I'm basically like getting this quasi-static picture.
But maybe very stupid question that I should ask in the beginning, but how can it possible? We have 2 particles in one frame, and one acts on another, accelerating that. This means that in this frame, the second particle should be accelerated. So
in the rest frame, right? In the left, right?
Yes. So they are not in the.
No, you're just an observer in the rest frame, right? So in the rest frame, like you just have your maximal system, and that's it. And you're still like in the rest frame.
Okay.
So what I'm doing, I'm just saying that I don't care about any waves that are traveling with the phase velocity, which differs from the phase from the velocity of those 2 particles. And just because I have this synchronism, I have the first particle, the wave, and the second particle traveling with the same velocity. I'm basically cutting out the the range of the solutions. So I'm narrowing them down just to solutions with a fixed phase velocity, which is fixed by those 2 particles. Does this make some sense?
Mm-hmm.
So
I guess there are some questions from the audience on Zoom. So Andrei, please, do you have a question? Or maybe Losha? Yeah.
Yes, thank you. Could you comment one more time about these red lines in this left figure, or maybe on the previous slide?
Oh yeah, so you have a Cherenkov effect, right? So and you have a shock wave.
Yeah, I have a shock wave, but for the reflected wave, it won't be a wavefront.
There will be some sort of a wavefront. I mean, obviously you'll have like. So the maximum. So
I mean, you see, from the beginning, you said that you are dealing with full wave solutions.
Okay, I'm sorry. Say it again.
As far as I understood, in the beginning, you said that you are dealing with full wave solutions.
So.
Yeah, and what kind of red line is what do you mean reflected? Maybe on the previous slide you can turn back.
Well, yeah, please. So
Stanislav, there is a total internal reflection as far as I know.
Well, yes, I mean, because, listen, so the black line here is basically, I forgot to mention this. So the black line here is perfect metal.
Okay.
So does this make a bit more sense right now? Just because it's a perfect metal, so you have the reflection, right, of all the waves.
I see. So it's some imaginary line.
Yeah. Okay. So this is basically the line shows you the in the reflection. So it will show you roughly the maximum of the field. So there will be like quite not very complex, but quite some picture after the reflection. So you'll have a phase flip and some other things going. So this red line is just to guide the eye, you know, just to say, okay, so you have your Cherenkov front, and then it's going to be reflected back, and then it's going to be refocused just because of this reflection to this, you know, another vertical line where you probably want to put your trailing particle. So yeah, because once the cone is reflected, so you'll have a phase flip, and then instead of decelerating field will this red vertical line, and the second vertical line will become accelerating. So it will change the phase.
So you don't mean here that somewhere you don't have field and somewhere you have field. So the field is everywhere.
Oh yeah. Behind, well, in front of the cone there is no field. But after the reflection, the field is everywhere, right?
Okay.
No. So I'm gonna talk not about the basically the whole thing which is happening behind the particle. So what I'm interested in is what is the field on the particle itself, right? And that's why I said it's like some sort of an idiotic consideration. So you say that your particle is driving with the speed of a light, so no field in front, no field behind. So everything is in this delta plane, which is traveling with the particle, right? So the charge density is given by, you know, the product of 3 deltas, and zeta is basically my coordinate, which I want to switch to because I say that this is my, it's not my frame, but that's my assumption about the electromagnetic waves that are generated by the particle. Because the particle is only coupled to the waves that are traveling with the same speed, with the same phase velocity. So I'll just, what I'm gonna do here, so I'm gonna take, so this cross section right here. So this is, imagine, so this is like what, Z, say ZX cross section, right? And I'm considering like XY cross section, which includes this particle, right? So, and then I'm gonna just rewrite Ampere's law. And so you have the circulation here along the metal sleeve, you have the flux going through the dielectric, and you have a flux going through the vacuum here. So S orthogonal, basically this cross section right here, which includes the particle. So now the consideration is like that, because it's a shock wave, right? So here, because the phase velocity is less than the speed of light, no field, right? Nothing, I mean, like by the definition, I just said because I have a Cherenkov effect and I'm traveling about the threshold. So this guy will go to 0 because magnetic field here should be 0. So here, the flux through the dielectric have to be 0 as well. So what we have left with is we have the integral from the EZ over the vacuum cross section, and it have to be equal to the charge. So the interesting observation here is that EZ, it's purely from the radiation. So that's the radiation field. So it's some sort of a reduced form of the Gauss theorem. You can get it straight out of the Gauss theorem, like, you know, with more or less the same considerations. The other part is another Gauss theorem for the magnetic field. So I want to stress that those are integrals over the vacuum cross section, so over the vacuum channel cross section only, and those components EZ and HZ are purely so the nature of those components are purely radiating. So those are from the radiation. So from those considerations, I've made no assumptions on like what type of radiation. Like, I mean, anything that will retard the field will produce that sort of a result. So if I can use this reasoning for some other problems, then the result will be the same. More importantly, So if you have a field penetration, say in this region, if it's not Cherenkov effect or the picture is slightly different, just because if you don't have charges, real charges here at the boundary, which is usually not the case. So you can basically throw away this flux. You can zero out this flux through the medium. And then instead of having equality here, you will have inequality. So this formula kind of gives you the upper bound always. So for the EZ, so the flux of the radiative field from the vacuum cross section will be less or equal to the charge always. That's what I think, and that's what I observe at least for the Smith parcel, for the Cherenkov, for the plasma waves as well. So that's some sort of interesting observation, I guess, and that's how you basically estimate the upper bound for the gradient, because your gradient cannot exceed the loss, right?
So the gradient along Z, right?
Yeah. Well, yes, for the gradient along Z, obviously, because the integral. I mean, like, listen. So this is an integral, right? So you can't say anything about the distribution, right? So, and if your channel has some tricky cross section, if it's not trivial, then you can't tell much about it. But it turns out, so because what I'm doing here, I'm saying that, okay, so at this point, like the full field have to be zero, right? Some combination, so nothing can penetrate inside like the medium. That's kind of the idea here. So if I look at the Maxwell system in the vacuum, so I can, like, after some manipulations, I can reduce it to something like that in a complex form, of course, right? So that's this E would be the complex function EX, EY, right? And this G will be a combination of EZ and HZ. Well, the derivatives by this zeta, which is Z minus CT, but still. What you observe here is basically that this GZ is some sort of an effective field, effective plane field. And the whole problem is actually plane problem. We know how to solve this problem. This problem is solved usually using conformal maps. So, and because I know the solution, and it's, I will not stop on this right now, but it's more or less a very simple thing how to solve the problem when you have like a circular cross section and you have a charge which is placed at the center. So you can almost trivially deduce it from either Gauss theorem or any other rationale. So once I have the reference, which is this, I will build a conformal map, which will map my source to the center of the circle and this area to the area of the circle, so to the disk. And then after some manipulations, basically, I will have that. So I'll have that EZ is basically 2Q over A squared, and the form factor will be defined by the conformal map. So HZ will be the imaginary part, well, again, of the product of two conformal maps.
But just to make it clear, you're now trying to solve the problem, find the field in the cross section, right? That's what you're what we're trying to do, right?
Yes. I'm not solving behind, so I'm just trying in the cross section. It's answering your question. You said like, okay, so it's on the axis.
No.
So any other point, like beside the point on the axis, in the cross section could be solved this way. So you can use conformal map because it's a plane problem, right? Mm-hmm.
Yeah, but then a question: when you do the conformal map, what happens with the dielectric? So you also have
nothing, because see here the effective condition that
you say that is zero, right?
The fields have to zero out, so there's no penetration inside.
Oh, okay.
So I'm using this, see, like this cartoon. So I'm saying like, okay, so my assumption that
so we have something like perfect electric magnetic conductor, right?
Right. So and you can always say that, because like in most real cases it's not perfect, but not perfect means that it will decrease the right hand side in this integral, and just because it's decreased, this whole thing will be always an upper bound. So like neglecting this part just just increases the so it's this estimate always holds.
And F is the transformation from your geometry to a circle.
Right. So this is this map. See?
Yeah.
So like from my arbitrary geometry to the circle such that so omega naught, which is the position and the geometry of interest, to the center of the circle.
Okay.
That's basically the result. So the way it is. So the wave potential then could be always presented this way, and that's kind of like the final result here. So you have the form factor, and you have one over the characteristic size squared. So, and the transverse wave potential could be always estimated this way. So those two formulas, they kind of, so if you will try to apply them directly to calculate the radiation and to do some sort of like real math, like I'll try to work with some experimental data, obviously this will be an overestimate. Usually the accuracy of those formulas for more or less realistic applications is about, I'd say 15, so they give you like a 15% error, which is not that unreasonable, and included and taking into account the simplicity of the formulas. Maybe it's not that bad as a good starting point.
But the discrepancy comes from the finite penetration, or
the discrepancy comes from the finite penetration, from the wave effects, and from all the complex things that I've omitted. So essentially, what I've done, I've omitted the properties of the material and what is happening once. Okay, so you generate your wave, right, and then there could be some interference between different harmonics, obviously, and those things they're not accounted for. So that interesting. So if you will just get rid of them, you can always get this, and this will give you an upper bound. So that's what I find important and interesting about that type of this sort of an approach. Knowing the upper bound, and this is an upper bound for the amplitude of the Green's function, meaning that you can't get anything high, right? I can convolve it, right, and the convolution is trivial for the case of the WZ. So it's going to be just the integral from the charge density distribution, right? So literally, so 4q over a squared, and then this form factor will give you the upper bound for the gradient, for the maximum field behind that you can have. So modulus will give me this estimate, which is cool. So now I know what to expect, and now I know that my optimal geometry is circle. If I choose any other geometry, I will lose because those two conformal maps, and we know, right? So there's a theorem in a complex analysis that says that, well, I'll just summarize it here. So that this factor will be maximal only when you have a circle. Any other maps will have the factor, this real part of those two derivatives will always be less than unity. And the other thing is basically everything is proportional to the size. Inverse proportional to the aperture squared. So the smaller the size of the channel, the higher the field. The higher the charge of the driving beam, the higher the field. Linearly with the charge and inverse squared with the characteristic size. Meaning that, okay, so millimeters will roughly give you what you want, right? So 100 megawatts per meter. And we know that millimeter size capillaries usually, realistically, what you can do. So it's a terahertz range. So that's, I'll try to connect it back. Okay. And basically for any medium, this estimate holds. So that's what I was talking about. So it's 2q over a squared, and f is the form factor that is deduced from the conformal map. While the transformer ratio, I will probably briefly talk about that. So I'll try to wrap it up, and then I'll just briefly show all other 40 or 50 slides that I have, and we'll conclude and we'll switch to the questions. So the transformer ratio is another thing, right? So I mentioned that the ratio between the EZ minus and EZ plus, so the higher the ratio, then the higher the energy of the trailing beam. Indeed, very simple toy model. So how you can actually estimate, so how you can connect. Obviously, intuitively, you may say that, okay, so probably I can't make very large R and keep EZ plus large at the same time. That's at least what my intuition was telling me when I was looking into this problem. So, and that's the formal definition. So R, the transformer ratio, this ratio is basically the maximum EZ plus, which is the field behind the beam, to the maximum EZ minus. How we can approach this? So I'll just skip all the tricks. I said that I will just express one through another. And basically, I consider a very simple example. I said that my Green's function, so I have a radiation like which has only one single harmonic. And then like I solved this, what's that, Voltaire equation, right? The integral equation, you just reverse it using known formula. And then like after some tricks, you can actually connect the maximum gradient to the transformer ratio. So what happens, interestingly, that if you try to increase the transformer ratio, so to actually accelerate the trailing beam to the energies way higher, so you have to pay the price. And this price is the gradient. The cool thing that's if you combine these results with the Gauss theorem that I showed you before, you can actually arrive at this formula to the right. So this formula basically tells you that you have a form factor here, okay, obviously, and then you have aperture squared, and then it falls back as 1 over r for the large r's. So, I mean, I've done some estimations. It was a lot of fun when I talked to Argonne people. So their first initial design of their machine, they were saying like, okay, we're gonna do like what 150 or 120 megawatts per meter, and the transformer ratio they claimed is gonna be 5, right? So if you take this formula, plug all the numbers, you'll get like 109. that's the power of this formula, right? So they have some intuition and they say, okay, roughly we should have some parameters like that. And then like what was deduced, it's like the upper bounds, the ultimate upper bounds. And you show like, no. Your upper bounds are actually less than what you expect. And that's basically like why you care about those like trivial calculations and things like that. All right, so I'll just tell you that the whole thing started in 1988 or even before. So the first experiments on the Wakefield acceleration were done at Argonne. And those are the 2 papers you can look at. So you have to have, as we said, like high gradient and high transformer ratio at the same time. So, and then you'll have your efficiency, right? Because then you can have like a low energy, you start from low energy and then you go to huge energies at a small distance, presumably. So for the high gradients, right now we have like guys from Slack, they showed like 1 gigawatt per meter. Well, it's a bit of a stretch, but still they showed it. So plasma people, they showed about like 42, and it was about 50 gigawatt per meter. So, and one is Nature Communication, the other is Nature. So the transformer ratio, so Argonne showed in structures, it was about 5, so that's experimental result. And in plasma, like 3 groups. It was what, like 2018, just one by one, they showed like, they published several, like 3 papers, and they showed the transformer ratio about 5 as well. The efficiency, nobody have done that, so nobody have combined those 2 things. Is it for a reason? No, I don't know. People are working on that, so that's a blank slide right here. So what are the challenges and what are the problems? Okay, very briefly, so I'll take another 3 or 4 minutes of the seminar. Obviously, the toy models and those like stories that I don't know if you believe them or not. I was telling you that you can accelerate particles in a short distance to huge energies. Well, I've considered very simple toy models, right? So the main problem there is the stability. That's a dynamical system. So you have huge fields. Actually, nothing is glued right straight there. So you have motions of both beams. So while you have longitudinal component of your Lorentz force, you have a huge transverse component of the Lorentz force. So both beams will blow up because of its tiny asymmetries. Actually, what is happening? So even if you'll just consider one dry beam, which is like here is presented as a chain of particles. So like a tiny displacement from the center has an exponential instability, basically because of the convolution term. So this is the very, very simplified equation of motion. So you have your focusing system, which is trying to keep your beam in place. And the right-hand side is basically the transverse Wakefield, which deflects the beam because of small displacements and of the symmetry of the problem.
Excuse me, may I ask a question?
Absolutely.
So the general idea, you want kind of create a very short accelerator, which can give you a very huge acceleration. So is it possible to somehow estimate time for this instability? So okay, you understand my question?
Yeah. So basically, you see, there are some letters here, right? So some estimations were done. So, and this is the real problem. So I've done those estimations, and it turns out that there's a huge trade-off, right? So you want to like high acceleration rates. So then you just limit it. So you're limited technologically. You're limited from the perspective of like how strong the focusing could be. So usually the focusing is accomplished using the magnets, and like the maximum magnetic field that you can achieve is what, like 1 Tesla at a tip. Like, and for superconducting magnets, probably even higher, but it's really challenging to create a superconducting magnet with the like 1 millimeter aperture. So it's almost impossible. Meaning that we are limited about like 1 Tesla, right? Which in ideal case will create like a magnetic gradient at about like 1 Tesla per millimeter, which is roughly 300 megawatts per meter. Roughly thinking that the transverse force is almost the same as the longitudinal, right? So to compensate for the deflection, so you have like 300 megawatts per meter, which is a big limit, right? So it's not that much. On top of that, there are other factors, and 300 megawatts is like probably like optimistic, like more realistic. You're usually like, if you consider like the real design, the machine will be like 100, 110 megawatts, and that's the limit of the magnet. And that's where you can fight the instability. If you go further, well, you don't know what you'll get.
So I can't analyze correctly. So where is the instability coming from? So L node is the length of a, what is?
Why it's what?
So I can say what is accumulating here?
Oh.
Gamma contains Z. Which is
no. Look. Yeah. So it's very simple, right? The head particle acts back from the second particle, right? And it basically kicks it, right? No, kicks it. Okay, so it's more or less linear effect. The second particle acts on the third particle, and the first particle acts on the third particle as well. So the further you go to the tail, the more the whole thing accumulates.
I understand the physics. Can you say a few words about gamma? You say that there is exponential term gamma. So it's y coordinate exponential increase, right? Is that the problem?
Yeah. So while you propagate, so you have exponential increase, but this is at the tail, so not the head.
Right. So it's exponential increases with z, right?
No.
With which?
Yeah.
Like relative to which argument it's
z. So the distance, the propagation distance. Because here, so here we have a lot of letters, and well, I guess L naught is the oh yeah, you have the z. No, you have the z. You have the z.
Yeah. So this has basically you have to prepare short like trails of these particles, and then that's it. So you're in terms of the.
Well, if you make it short, then you're losing some other important parameters. So because
which ones?
For instance, here, right? So if we talk about, we briefly talked about the transformer ratio, right? The transformer ratio, it is defined by the length here, right? So I was saying that L is the length of the bunch, right? So you want to have the high transformer ratio. So then you see KL, right? Mm-hmm. So the higher the L, so it's linearly proportional to the length. So I mean, you make it short, you lose the transformer ratio, then you lose the efficiency, and then what you have, and that usually people use from time to time, so is that you just transfer the energy from the first beam to the second beam, and then you increase the energy of the second beam, not just the energy of the first, right? Mm-hmm. That's not very efficient, and that's not the dream people are pursuing, because then from 100 you have only 200, mm-hmm. not 1 GeV, which makes the machine again longer, because you still want to reach the GeV. Mm-hmm.
I guess
I had the same question as you.
So, okay, so let's go briefly here. So there are tricks, as I said, right? So you can do some things like you can compensate for these effects, because mostly this is a weak resonance. So, and you can cancel it out by detuning the whole beam from the resonance, usually by introducing the energy spread or some other tricks. But it turns out that, again, like for the case of the Wakefield Accelerator, the energy spread have to be considerably larger than in conventional machines where people do these tricks. So it's still something that needs to be studied. The energy spread, that's some other problem. If you want a collider, you probably want to have a mono-energetic beam, because if you don't have particles with the same energy, you'll have problems with the dispersion. And well, if it's not a collider, if it's easier to understand if you build a free electron laser, right? So if you don't have a narrow spectrum of your lasing beam, then you don't have a narrow spectrum in the immediate radiation. So where it comes from? Well, much probably it comes from just the non-linearities of the field itself. It's a general problem, so you have to find it somehow. People suggested several things how you can do it. So basically, again, using the Wakefields, you can remove the residual energy spreads. So people have done this like a linear and even some sort of a non-linear regime. And this is more or less subtle thing, I guess. But it's still a challenge, and I don't think that anything more or less reasonable was shown experimentally. I think recently plasma people have published some papers, but just probably this year, I think. So yeah, so plasma have done this, and yeah, okay, so my conclusions. You can read them here, so it's very simple. So I will just highlight that there are a lot of technological challenges, and there are a lot of conceptual challenges. So what I've showed you is just like some idea of what the field is. So the main direction right now, people are working on plasmas, and just because of the fact that the radiance is way, way higher, plasmas are very difficult to control, and it's a huge, engineering effort to build actually like a plasma cell and to control it. But it turns out that it's more perspective than it has more perspectives than just to use structures. There are still some developments for the structures at Argonne, so it's the main place where people are looking at the structure-based acceleration. I'll take any questions right now. So
yeah, so I guess there was some question. Lyosha, please.
Yes, thank you. I just have a couple of questions about what is going in this field. So is there any works on structuring these mirrors? Can it help maybe to shape the gradient or something else? Because what you showed and what you considered in your theoretical result is just plain mirror with dielectric covering.
mm-hmm. Well,
and the second question maybe immediately. So in fact, you considered that the first particle which accelerates the second, they don't have how it is say effect of the second particle on the first one. But unless the motion is less than the speed of light, I think we can imagine mechanism of organizing this again self-action. So is it a way that could help to find new designs?
well, see, the problem is that. So I'll answer your second question first, right? And then we'll go back to the first one. So the problem with this is that usually, no, there's no action from the second beam on the first beam. It's almost impossible. So the separation is quite large, right? And I mean, terahertz, the period is, so the distance, right? So if you think of like a terahertz band, right? So the distance between, and then that's one wavelength, right? At least, maybe usually it's two wavelengths. So then this means that the distance between the first and the second beam is very large, and your characteristic size is 1 over gamma, right? So there's no back action. It's just literally no, in any experiment related to those things, no back action.
Yeah, I mean, can we imagine some new design to organize this back action?
Well, no, because you will go to so you will use ultra-relativism, and the intensity will go down. So if your particles are non-relativistic, then the intensity of the radiation that you're trying to create will go down, right? So there's a dependence on the gamma. So there's certain saturation. So when you go to the relativistic regime, you reach the saturation, in terms of the power, radiated power, right? So, and if you go like down, then you start losing, and you may lose dramatically. The other problem is that you don't have a decoupling between the longitudinal and transverse momentum anymore. So you will have a very complex dynamics, which is, I mean, you know, the space charge, right? So the Coulomb interaction, it's a nonlinear interaction, and any nonlinear potential has like all the problems with the resonances. So you will be, I mean, now playing in a different field, nonlinear dynamics. It's possible, but it's just hard to tell. The other problem with the nonlinear dynamics is that you will always have a so-called, well, you'll always have a frequency spread, right? So you'll have different frequencies now, and it will be almost impossible to have a, how to say it, if you're familiar with emittance, right, or like this, the phase space, right, of the beam, like fixed. So you will always have this mixing, and it will be really hard to control the size of the beam in the phase space. So you want to, the smaller the beam you have, the better, because then the interaction cross section becomes larger. But if you have large beam, right, so you want to have not just intensity, but intensity in a phase space, so which is usually called the small emittance. So I mean, I don't think that, maybe for some applications that make sense, but not for the high energy. That would be my my answer. And the first question was
structuring of mirrors.
Mirrors. The structures, as I said, are like less of an interest right now, just because of some more or less obvious limitations with the structures. So when you go to the high gradients, it's not only, I mean, technological challenges, how you're going to build it, how you're going to machine it. It's all other problems that comes with the materials, right? So you have a loss factor, you have heating. You have heating, then you think, okay, so how I'm going to, what a material I'm going to use for the mirror, right? So you have like a intense radiation, and if you have a focused radiation, then you'll have a pulse heating, and then you will just evaporate the mirror material. And that happens several times in several experiments with structures. And that kind of produces huge problems if you want to go.
You can take dielectric mirrors.
You can, but there's a certain breakdown in dielectric as well. Mm-hmm. And well, the only material which is more or less suitable and people seriously considering is a single crystal diamond, or polycrystal diamond, with a not that much poly, right? So of a, say, let's say, decent quality, right? So it's not completely single crystals, because sometimes it's very challenging to make single crystals. So with as less defects as you can make.
Maybe I have a very related question. So with this dielectric layer, you have a fixed epsilon, which actually can be arbitrary, but by proper again, I don't know, structuring it. So is there any sense in doing that? So having high epsilon, so having large angles and things like this.
Maybe, I mean,
because like in metamaterials, you can reach, especially in that region, you can reach any epsilon you want.
Metamaterials, if you talk metamaterials makes more sense in you see, you can, as I said, right? So like this analysis, it did not include the all those tricks with interference, right? People, what people do with metamaterials and what they're really interested in is that, okay, so if you look at the spectrums, so the longitudinal part of the Lorentz force has one spectrum, and the transverse force has a different spectrum. What people are trying to do, they're trying to manufacture a material with a band gap, which basically kind of like cuts out the frequencies, the dominating frequencies of the transverse force. And that's how they suppress the effects, the unwanted effects of the transverse force, and that's how they reduce the amplitude and suppress the instability. That's something people are working on actively right now, and that's what is kind of interesting, I would say.
I have a couple of questions. Did I get it right that one of the things that will improve the acceleration is the ratio between the charges of the two particles?
Not the charges, but the ratio between the decelerating field, right? So the average field on the beam that decelerates the first field, and the accelerating field that acts on the trailing beam. So this ratio should be maximal.
Okay, yes, I see. And I also had one more question. It's maybe a little bit silly, but if we somehow prohibit the propagation of electromagnetic waves in these dielectric phasings in the backward direction, will there be any interesting things?
It depends on what wave, right? So like if you will restrict waves with certain components, as I said, right? So going back to this discussion about the band gap, yeah. So if you like, like what causes, like if you just solve the problem, the electromagnetic problem, the Maxwell system, right? You will see what contributes to the transverse particle Lorentz force and what contributes to the longitudinal part. So those waves are kind of different waves, different types sometimes, right? So for example, in the cylindrical structure, you have like TM, right? And those modes are usually accelerating modes. And then you have hybrid modes. Hybrid modes, you don't like them because they have the transverse, so they contribute to the transverse Lorentz force. So if you can prohibit hybrid modes, and people are trying to do this in some sort of a like naive way, but yeah, then you're good. This makes a lot of sense.
Okay, thank you.
So maybe a general question. So I wonder if any quantum effects are playing the role in these Wakefield accelerators. For instance, I can imagine that since it is important to minimize instability, so you try to center the electron exactly in the center of this waveguide, this structure, and then due to uncertainty relation, there might be some, intrinsic limits of instability, how much you can suppress it, let's say.
Usually, well, obviously you're right. So nobody can hit the point, right? Yeah. So the probability is 0. So that there's always like some, error. So people like account for the errors. So these errors basically they you kind of go backwards. You say like my tolerance is up, right? So when you build something, you say like okay, so my tolerance is like I don't know, like 100 micron. And you go to the engineers and say, like, can we do it within 100 micron? And if we're talking about like 10 centimeters, they will tell you yes. We're talking about half meter, I'll tell you probably no. They will tell you that it's very challenging. So then you take the tolerances and you propagate them back and you say, okay, if you have those tolerances, what kind of instability you have? Will it work? Will it not? So that's basically it. So that's the way people usually consider it. No more than that. Because, you can't do much about it, so you don't have much of a control of this instability. So the only thing you can work with in structures is magnets. There should be certain, so I would say it's not quantum, right? It's more like a dynamics in a wide sense, right? So you have a collective motion of an ensemble of electrons. So and you want to think what you can do, how you can prepare, say, a distribution of those electrons in the phase space that will help to mitigate the instability. Because the instability in the first order, it's a linear effect, so it's just a linear resonance. But then you may introduce some nonlinearities, but nonlinearities will ruin the emittance and will ruin probably the luminosity of your machine. There's a certain interplay, I would say. And it's more like about the dynamics.
So far from any quantum mechanics yet.
I don't think that they play an important role. Although, let's put it this way. So if we talk about the plasma accelerators, right? So they are going further and further with the gradients, right? And their dream and what they're trying to accomplish right now. So they want to create two approaches, right? So they either want to create like a very cold beam, right? So when you put electrons very close to one another, and then you have your column field close to the Schwinger field. And then they want to do like they are dreaming of creating electron product from plasma, but I think it's all how to say that I don't really believe that, right? So the other thing is, which is more reasonable, is that you tweak the parameters of the plasma and you set up your plasma experiment when you again like approach very high fields. So it's a high field, like if you want to so maybe like some quantum electrodynamics in the high fields. That's what you may observe, but it will be more like a byproduct and some experiment based on the device rather than an effect that will contribute to the performance of the device.
Okay, thank you so much, Stanislav. I don't see any other questions from the audience. So